This information is presented by Bluewater Auto Restoration.
Welcome back. This is week 23 of the 2026 Bluewater Auto Restoration podcast. We release new podcasts every Saturday morning. In this deep dive, we look at 3D scanning classic parts for reproduction.
It's a fascinating topic, really.
It is. I want you to imagine a library burning down. But instead of books, the shelves are just filled with the physical legacy of industrial design.
Oh, wow. That's a visceral image.
Right. Every intricately machined gear train, every hand-rolled, sweeping fender of a pre-war roadster, every impossible mechanical casting from the last century.
Just gone.
Gone. And the true catastrophe isn't even just the fire, it's the realization that no blueprints ever existed for most of this inventory in the first place.
Yeah, the master craftsman who shaped that metal is long gone.
Yeah, exactly. The factory was bulldozed decades ago, and the original tooling has just rusted back into the earth. So our mission today for this deep dive is exploring the technological revolution of reverse engineering.
Which is really the ultimate collision of the past and the future. Yeah. We are looking at how cutting-edge lasers and advanced algorithms are rescuing irreplaceable classic cars, obsolete machinery, and even ancient history from being completely lost to time.
Because we aren't just talking about taking pretty digital pictures. We are talking about mathematically resurrecting physical artifacts that literally have no underlying data.
Pulling manufacturing data out of thin air, whether you're in the trenches of MRO, maintenance, repair, and overhaul, or you're a restoration specialist trying to save a classic car, the way we capture the physical world has fundamentally shifted.
It's a complete paradigm shift. But, before we can appreciate the magic of 3D scanning, we really need to understand how painstaking and flawed this process used to be.
Oh, the dark ages of reverse engineering.
Exactly, the dark ages, because recreating a broken or missing component was, well, it was done entirely by hand.
I can't even imagine.
It was a nightmare. You would use dial indicators, calipers, radius gauges, and modeling clay.
Wait, modeling clay for precision engineering?
Yes, literally industrial clay or plaster. The end result was usually just something similar at best. It was never a perfect replica.
Okay, let's unpack this for a second, because if they were just relying on hand calipers and clay, how did they ever get the tolerances right for something as precise as, say, a combustion engine or a complex chassis assembly?
Well, what's fascinating here is they often didn't.
They just guessed.
Essentially, yeah. Manual methods naturally led to poor dimensional fidelity. Plus, you have human error. And furthermore, it was nearly impossible to accurately capture free-form surfaces.
Like organic shapes.
Right. Compound curves or hard-to-reach features, you just couldn't measure them accurately with a straight ruler.
And what about scale? Like, for large classic cars, what the European restoration market calls old-timers.
Oh, for those, mechanics actually used to build physical stencil frames.
Physical frames, like out of wood.
Exactly. They would place a massive wooden box frame completely around a vehicle, and then they would graphically scan it, slice by slice, with physical rulers.
So they're taking depth measurements from the frame to the car every few inches.
Yes. And from those cross-sections, they would build wooden skeletons to mimic the car's shape. Then a metal worker would hammer flat sheet metal over that wooden buck.
That sounds incredibly labor-intensive.
It was staggering. And again, the accuracy was entirely subjective. It depended entirely on the skill of the guy with the measuring stick and the guy with the hammer.
So these analog limitations must have created a massive bottleneck in the industry.
Oh, absolutely. The pain of this bottleneck forced the industry to look for a missing link. They needed a digital bridge between physical reality and manufacturing.
Which brings us to the digital translation. How do we actually turn a physical object into a newly manufactured part?
We move from the why to the how. And the modern scan-to-CAD workflow is, frankly, a revelation. It's a fast, multi-step process.
Walk me through the steps. What's phase one?
Phase one is capture. You scan the broken or existing part using handheld metrology scanner.
Like the small GOM scan one, right? Or
Yeah.
the Einscan Libre.
Exactly. These use structured light. Instead of just taking a photo, they throw a rapid sequence of precise light grids across the object. This capture phase takes minutes, not weeks.
And that generates the point cloud. Just millions of floating data points.
Right, but a raw point cloud is useless for manufacturing. So phase two is mesh generation.
Where the software weaves those points together?
Yes, the scanner converts the point cloud data into a watertight mesh, typically an STL file. And modern scanners use really powerful onboard processors like NVIDIA chips and touchscreens to let users clean the mesh right on the device.
Okay, so it's basically like taking a physical object, running it through a real-life translation app to turn it into digital math, and then hitting print to bring it back into reality.
That's a great analogy. But there's a crucial middle step before you hit print. Phase 3 is CAD conversion.
Right, because an STL file is just a dumb shell. It doesn't know what a perfect cylinder or a flat plane is.
Exactly. You transfer the mesh into dedicated software like XModel or GOM Inspect to repair the component digitally. The software layer is really the unsung hero here.
Because it bridges the gap.
Yes. It allows engineers to not just copy a part, but, actually extract the design intent. Say you have a broken impeller. You can digitally repair it, make it perfectly symmetrical again in roughly 2 minutes.
You can fix the 60 years of wear and tear before a single drop of metal is printed.
Precisely. You run stress analysis, modify dimensions for better performance, and then phase 4, you manufacture it. Send that perfect CAD file to a 3D printer or a CNC machine.
So the theory sounds great. It's seamless. But I want to know how this holds up in the real world when dealing with incredibly rare, complex, and high-stakes historical artifacts.
The ultimate stress test.
Exactly. Let's look at the automotive world, specifically a 1937 Ford Eiffel.
Oh, the ClassicCar.TV project. That is a brilliant case study.
Yeah, for you listening, ClassicCar.TV reaches something like 300,000 readers a month, and they wanted to digitize this totally unique 1937 Ford Eiffel.
And what made this car so special was its custom Glazer chassis. It was basically a one-of-one bespoke coach build. If that geometry is lost, it's gone forever.
So they took this car to the Makerspace high-tech workshop at the Technical University of Munich.
Right, and to capture something of that scale and complexity, they couldn't just use one tool. The process required 2 different scanners.
Because you have competing needs, right? Big panels versus tiny interior parts.
Exactly. They used a broader scanner, the Artec EVA, for the expansive body surfaces, the interior, and the wooden ladder frame.
And for the small stuff.
They switched to a detail-oriented scanner, the Space Spider. They used that for all the disassembled, hard-to-reach parts in extreme high resolution.
But wait, scanning an entire car usually presents a massive optical problem.
Specular reflection.
Right. If you point a light grid at a shiny chrome bumper or a glossy paint job, the light just scatters everywhere.
It blinds the cameras. Usually the workaround is spraying the whole car in a temporary chalky anti-glare spray, which is a huge hassle, especially on a priceless classic.
But they caught a lucky break with the Ford Eiffel, didn't they?
They really did. The car's body was mid-restoration, so it was covered in a matte anti-corrosion primer.
The optical holy grail.
Exactly. Perfect capture conditions. No anti-glare spray required.
So they capture all this data. But scanning an 80-year-old car creates an enormous bulk of data.
There's a massive bottleneck. Data management is critical. You need incredibly powerful computers.
If you aren't careful, you'll just crash your system trying to stitch it all together.
The true skill lies in capturing just enough scans to build a 3D model without overloading the software. But they successfully fused the scans in Artec Studio.
They fixed the holes, created a full point cloud, and actually made a 1.4 scale 3D printed model, right?
Yeah, it was shown at the Future Meets Past exhibition. They also generated data for sheet metal dies.
But here's where it gets really interesting. It's not just about copying what is there. It's about mathematically recreating what is missing.
Oh, you're talking about the retractable top.
Yes. The original top was completely gone.
Right, there was nothing to scan. But based on the surrounding geometry, the hinge mounts, the windshield curve, they completely reverse-engineered a missing retractable top in CAD.
They mathematically hallucinated a ghost part. That is wild, and we see this in other automotive jewels, too.
Absolutely. There was a unique Fiat 600 Elaborazione Frua, designed by Pietro Frua. It had these bespoke turn signal mountings on the fenders that were totally missing.
And they reconstructed those completely via scanning the fender's curve.
Exactly. And a 1995 Porsche 993 was successfully reverse-engineered for restoration down in Spain. The applications are everywhere.
Okay, so scanning a tiny turn signal or even a compact vintage car in a pristine Munich laboratory is one thing.
Right.
But what happens when the object is massive and you can't move it? I want to talk about size and scale constraints.
That introduces a whole new tier of difficulty.
Because there's a company in Bavaria called 3D EAS. They were tasked with digitizing the vehicle frame of a 1961 BWAR.CA's B1000.
The East German delivery van. The frame on that thing is massive.
Huge. It was 6 meters long and 2.5 meters wide.
And the required accuracy was brutal. For the axle beams, they needed a microscopic 0.05 millimeter tolerance.
50 microns over a 6-meter span.
It's incredibly tight. Previously, to do this, they would use a measuring arm with a laser attachment, a CMM arm.
The old tool versus the new tool.
Right. But for a 6-meter frame, an articulated arm is a nightmare. It's too rigid, it has a limited physical reach, maybe 2 meters, so it required constant, exhausting repositioning.
They call it leapfrogging. Right, you unbolt the arm, move it, bolt it back down, recalibrate.
And every time you leapfrog around the object, you introduce a tiny mathematical error. It compounds until your 0.05 millimeter tolerance is completely destroyed.
So the legacy workflow just failed.
It did. The solution was using a highly portable HandyScan 3D.
Which is an untethered handheld laser scanner.
Yes, and it has a 0.025 millimeter accuracy out of the box. The general manager of 3D EAS actually compared this leap in technology to racing.
How so?
He said this tech is to digitalization what Michael Schumacher is to racers. It's just in a completely different league.
Wait, let me push back on this because I'm trying to visualize this. So they just carry this thing in their hand luggage.
Literally, yes. It fits in a carry-on case.
How does a portable device moving freely through the air, vibrating in someone's hand, maintain 0.025 millimeter accuracy over a 6-meter span without losing its place in physical space?
It's a great question, because there are no physical encoders anchoring it to a table. The genius here is dynamic tracking and target markers.
Target markers, like stickers.
Exactly, little reflective stickers. The technician places them all over the frame and the floor.
Creating a constellation of reference points.
Yes. If we connect this to the bigger picture, the true revolution here is becoming completely size independent. The scanner's cameras track those markers at high speed.
So it's constantly triangulating its exact position in 3D space based on the stickers.
Exactly. It completely untethers the engineer from the metrology lab. They can now scan anything from a 3 by 3 centimeter component to a full airplane.
Outdoors or indoors.
Entirely on the customer site.
Which is just a staggering shift, because if this technology can flawlessly reverse engineer a 1937 Ford chassis or a 6-meter Barcus frame in a dirty garage, where else is this being applied?
Oh, the ripple effect across global industries is huge. We have to pan out and look at the broader implications.
Let's look beyond automotive. What about the maritime sector?
That's a perfect example. Outfitting yachts. A yacht has almost no straight lines.
Just massive compound curves everywhere.
Right. Historically, fitting custom carpets or upholstery meant technicians manually cutting huge cardboard templates outdoors on the deck.
Which is terrible because cardboard warps in the humidity.
Exactly. But now, they are scanning yachts outdoors.
Wait, I thought ambient sunlight blinded the scanners.
It used to. But modern hardware can filter out the sunlight. So they scan the deck and create perfectly custom-fit accessories in CAD, completely eliminating manual measurement labor.
That's incredible. And what about heavy industry? Or aviation?
Oh, rapid reverse engineering is huge there. We are seeing MRO teams scan and manufacture non-standard aircraft engine parts.
Just bypassing the traditional supply chain entirely.
Yes. And there's an organization called Blue Sky Rescue. They optimize the layouts in their emergency response vehicles.
By scanning the cavernous interior of the rescue truck.
Exactly. They generate a digital twin of the cabin and then computationally arrange the oxygen tanks and stretchers for maximum efficiency.
Shaving seconds off deployment times.
It saves lives. And in heavy industry, they are reverse engineering massive mining equipment.
Right in the dirt of the open pit mine.
Yes. If a cast iron linkage breaks in a remote mine, they don't wait weeks for a part to ship. They scan it on site and digitally fabricate a replacement.
The timeline just collapses. But let's shift to an even more difficult constraint, the human body.
The medical applications. This is truly life-changing.
Yeah.
We are seeing this streamline the design of prosthetics.
Because historically, making a prosthetic socket meant wrapping the patient's limb in wet plaster, right?
Yes, which requires physically pressing on the tissue. It's uncomfortable and inherently inaccurate.
But scanning is non-contact.
Exactly. Clinicians use handheld scanners to instantly capture the undeformed topography of the patient's anatomy.
So the CAD software can design a socket to perfectly match the patient, avoiding nerve clusters and bone prominences.
It drastically enhances patient comfort. We are customizing the machine to fit the biology instead of the other way around.
That is profound, and it doesn't stop with the future of medicine. We are actually using this to back up deep history.
Heritage preservation in science.
Let's talk about the oracle bones.
Ah, yes. In China, researchers are digitally preserving ancient oracle bone inscriptions. These are pieces of bone used for pyromancy thousands of years ago.
And they are incredibly fragile, I assume.
Extremely. If you try to make a physical paper rubbing of the carvings, you risk destroying the artifact.
So they scan them instead.
Yes, capturing submicron topography to create digital rubbings.
So a historian can study the microscopic tool marks without ever touching the actual bone. And the paleontology world is doing this too.
Yes, down in Argentina, they reconstructed a Cretaceous predator dinosaur, the Torivinator.
From fossils. But fossils are usually crushed by geologic pressure, right?
Almost always. So the team scanned the fragmented bones, they imported them into CAD, digitally repaired the crushing, and modeled the missing skeletal links.
Just like the convertible top on the Ford.
Exactly the same principle.
So what does this all mean? We've gone from a vintage Porsche bumper to the bones of a Cretaceous predator. It feels like we are literally backing up the physical world to a hard drive.
We are. Knowledge in physical forms are no longer lost to time. We are decoupling the geometry from the material constraints.
But this raises an important question about the future of how we manage stuff.
Oh, you're talking about the shift to digital inventory.
Yes. Are we entering an era where physical inventory is replaced entirely by digital archives?
It seems inevitable. Think about those massive climate-controlled warehouses corporations use to store obsolete spare parts.
Billions of dollars of metal just sitting on shelves.
Exactly. But if a part breaks in 50 years, you won't need a warehouse to find a spare.
You'll just query the database.
Yes, you'll download the scan, the CAD file, and print it on demand. Inventory becomes entirely weightless.
A weightless supply chain. Which brings up a really fascinating philosophical dilemma for the listener to ponder.
The ship of Theseus paradox.
Exactly. If we can perfectly, down to the micron, recreate any physical object from a classic car's chassis to a dinosaur bone, does the concept of a physical original lose its meaning?
It's a heavy thought. If we scan a resting artifact, extract its perfect truth into CAD, and the physical object crumbles away.
When we print a pristine new one, is it less authentic? Or does digitizing an object simply make its original blueprint immortal? Maybe the geometry is all that actually matters.
We are rendering the ghost immortal.
I love that. Rendering the ghost immortal, that is the perfect place to leave this. For you listening, I want you to remember to visit the BlueWaterAutoRestoration.com website.
Lots of great resources there.
Absolutely. And a quick reminder, our podcasts are available on Spotify, YouTube, Apple Podcasts, or SoundCloud. Thank you so much for diving up with us today. Keep looking closer, and we'll see you next week.